previous class we were discussing capacitors, combination of capacitors in series and in parallel, right?
Yeah.
Let us continue. That's over. Now today we'll see what is the energy stored in a capacitor. Okay. So let us start. So energy stored in a capacitor.
Okay.
So capacitor is a device which can also store energy in the form of charge. So how do we store energy in a capacitor? We store energy in the capacitor by charging it. So by charging, we do some work. We do some work, and that work is stored as the energy inside the capacitor. Okay. So we do work. The work done is stored as energy. Okay, like the potential energy, in the form of potential energy. Okay, so I'll give you the expression directly what the energy of a capacitor is. So it is denoted by U, which is half CV square. Okay, this is the most widely used formula, but by doing some tweaks we can also obtain some other forms of this formula. For example, we know that Q is equal to CV, right? So this C can be replaced by Q by V. So in that case we will have different forms. So other forms of this are like half Q square by C, and it is also equal to half into QV. These are all the same things. Okay, so this is the energy stored in a capacitor. There is another term that is widely used in case of capacitors, that is called energy density.
Okay. What is that?
Energy density. Energy density, what can you think of it? See, energy density is energy per unit volume. Like the energy in general is the whole energy of the capacitor, but this is energy per unit volume, which we will call the energy density. Okay, and that is denoted by small u, that is opposed to a capital U, small u, and that's nothing. See, if we see this expression, half energy is what? Half Q square by C. All right.
Yeah.
Now, if we replace from the capacitor, if we have a parallel plate capacitor, okay, like this,
Yeah.
then we can obtain the expression of the charge on either plate, which is q, let's say. So q on this plate, which is plus q and minus q, q on either of the plate is equal to sigma into a, okay. This sigma is the what, density,
Sigma, yeah,
okay,
charge density,
charge
right?
density, and a is the area. All right,
Yeah.
now this density can be replaced, not, yeah, so this density can be replaced by epsilon naught e.
Okay.
I think we obtained that expression earlier. Sigma is epsilon naught e
Yeah.
into a, so q is this. You can also you remember this if you get a question, or I don't know, maybe. So
Okay.
q is sigma a. Now if you replace this q with sigma epsilon naught ea
Yeah.
in the expression for this energy, okay, u,
Yeah.
capital U, so sigma, oh sorry, epsilon naught ea square divided by the c. And what is
Yeah.
c? C, we have a, it is a parallel plate capacitor, all right. So the plate
Yeah.
capacitor has a capacitance of epsilon naught a by d, where d is the distance between the plates, a is the area.
Yeah.
So we have obtained this, okay. Now if you solve this, right, you will get something half epsilon naught e square ad. So half epsilon naught, because one epsilon naught will cancel, right, e
Yeah.
square ad, you will get this. This is the energy only, not the density, right? We are still
Yeah.
talking about the energy, but if you take this thing, which is a into d, if you consider this, what is a into d?
Yeah.
D is the distance, a is the area, and if you if you see, volume is what, area multiplied by the third like dimension, or you can say area into height is the volume, isn't it?
Oh. Okay.
Area
Oh yes, yes,
is
yes,
meter
yes, yes,
square,
yes. Yeah.
height is meter, so meter cube will be the volume.
Yeah. Yeah. Okay.
So what you do, you take this a into d and take this on the left hand side, and then when we do this, we will get in the denominator, okay. Half epsilon naught, just uh, we are just tweaking it, okay. So u upon ad is equal to half epsilon naught a square, and this, which is a small u, is in fact u upon volume, okay, because this is the energy per unit
Okay.
volume. So for a capacitor it is u upon ad, isn't it? Energy density.
So for capacitor, it's U upon AD, and
So u upon
isn't
ad,
it the same as?
this whole can be replaced by half epsilon naught e square.
Okay.
This is the energy density of a capacitor. You by you were required to calculate this u by volume for a capacitor, and that we have done on the right hand side, and then replace u by ad by this expression, because u by ad is energy per unit volume. So
Okay.
this u, which is small u, is energy density. This might be like joules per meter cube in SI units, okay. So
Okay.
you'll get some question on it maybe. All right.
Okay.
Now let us see an interesting.
Would you ask us to derive the formula for
No,
energy?
no, you won't be asked that.
Okay.
Now let us see an interesting problem, you can say. Redistribution of charge. All right.
Yeah.
Second, hold on.
Okay.
Two. For this, because this is in the syllabus. All right. We'll see what happens when the charge redistributes. Suppose we have two spheres. Okay, these are capacitors. In fact, these are two spheres, each one different radius. So let us say one of them is R1, another is R2. All right, and this one is having
Yeah.
Q1 charge. This one is already having, they both have some charge initially, right? Now
Yeah.
we are going to touch them, okay, but before that we want to see what is the total charge initially. So what is the total charge on both of them, which will be Q, let's say, which is Q1 plus Q2.
Yeah.
Okay, that would be how much? Q is C into V, so C1
Yeah.
V1 plus C2 V2. All right, now what we
Yeah.
want to do, we want to like connect them, okay. So we'll connect them and using a wire or some metal, whatever conductor, and we will see what happens to the charge that each sphere has, whether that changes or it is still Q1 and Q2 on each one of them, or whatever it be, like on the individual, because the total is gonna be the same anyway, right?
Yeah.
So let us connect them. Q1, let's say, after connecting, okay, so after connection, let's say this has a charge Q1 dash. We don't know, it may be equal to Q1. We are just assuming that it has now got a charge Q1 dash, because you know the redistribution may take place if it has some
Yeah.
more charge and it has less charge. Then what happens? We don't know. Like Q2, some Q2 might go to Q1 or something else may
Okay.
happen. Radius will still be R1. We are not writing it
Yeah.
R1 dash because that's a physical thing. Let's say this is Q2 dash and the radius is still R2, and this we connected them like this. Now what can you say about the charge on each one of them?
Is it still fluctuating?
See, what we need to see here is that when we connect them,
Oh, is
okay,
it a conductor?
yeah, only then the charge flow gonna takes
Oh,
place now.
okay. Yeah.
So that's why we connect. You can also join them directly, it does not matter, right? You can also place it like this, it's the same thing, okay. So you need to like see that after joining, the potential
Yeah.
of potential is gonna be the same, okay.
Okay.
Potential will be same for both. Initially they were having different potential, all right,
Yeah.
but since we have joined them, the potential, we will, after connecting them, will be the same for both, okay. So Q in general is equal to CV, right?
Yeah.
And if Q1 C1 V1 and Q2 C2 V2, that is it, that's how it
Yes.
is. But if this V is common, all right,
Yeah.
if this in both the cases is C1V and this is C2V, then the Q is depending on C1 and C2 only.
Yeah.
So can we say that when we join them, the Q, the charge on each capacitor Q, will be proportional to its capacitance,
Yeah.
because the voltage in fact is the same for both?
Right.
Now when this is true, we will get some interesting things. See, when this is true, like Q is proportional to C, that means Q1 will be some C1V and Q2 will be some C2V.
Yeah.
So can we say that if we divide both of these equation, all right?
Yeah.
But before dividing, let's, because we assume there's Q1 and Q2 dash, so let's call them Q1, and we are talking about Q1 and Q2 dash. So Q1 dash would be some C1V, Q2 dash will be some C2V. Okay,
Yeah. Okay.
so Q1 upon Q2 dash, like we divide the both equation. If you divide them, so that would be equal to C1 by C2. All right,
Yeah. Yeah.
and that further will be equal to R1 by R2.
Yeah.
Why? Because the charge of an isolated sphere is what? C is 4
For
pi
sure.
epsilon naught R. See, this is a constant. C is proportional to R.
Yeah.
So first we found that the charge distribution will be in the ratio of their capacitance after connection, right?
Yeah.
And that further will be equal to the ratio of their radii.
Oh, okay.
Okay.
Yeah.
Now also Q1 plus Q2 will definitely be equal to Q1 dash plus Q2 dash. This is a universal fact because no charge is spilling out
Yeah. Yeah.
anything, leaking, no leakage.
Mhm.
So the initial charge and final charge should be the same. Okay,
Yeah.
this is by the principle of charge conservation, same as that of energy conservation. Okay?
Yeah.
Charge can neither be created nor be destroyed. Now if we want to find individual, this is the ratio, okay, if you want to find Q1 dash,
Yeah.
then how can you find from this expression? If you know some algebra, you may give the answer to me directly.
Q1 dash is
See,
equals to Q.
Q1 dash will be some ratio of Q1 dash plus Q2 dash,
Yeah.
like some fraction of Q1 plus Q2 dash, isn't it?
Yeah. Yeah. Yeah.
So how that will distribute? See, Q1 dash upon Q2 dash is equal to C1 by C2. That means if we want to find Q1 dash, look at this expression, C1 upon C1 plus C2. Is the ratio correct in which I have distributed it? See, this is the whole charge.
Yeah.
Okay, we have divided this between Q1, we need to divide this between Q1 dash and Q2 dash. So Q1 dash will be some fraction of the total charge, and the fraction in the fraction, denominator is greater, numerator is smaller, isn't it?
Yeah.
For
Yeah.
example, it might be 0.5 or 0.4, like something like that. So this total C1 plus C2 we need to put in the denominator. This is from this equation only, nothing else, simple algebra.
Yeah.
So C1 upon C1 plus C2, this is the ratio that Q1 will have on its own,
Okay.
and the rest will be with Q2 dash. So what will be, again, that will be some part of Q1 dash plus Q2 dash, and Q2 dash will be proportional to
C2?
C2. That's
Yeah.
why C2 will be in the numerator and then the whole in the denominator.
Oh, okay.
This is the individual value of Q1 and Q2. Alright.
Yeah.
Now this further can be written in the form of radii also if we don't know the individual capacitance value. How? See how. Just you need to replace C1 C2 C1 C2 by R1 R2. That's it. Because C1 C2 itself is proportional to R1 and R2, isn't it?
Yeah.
It further is equaling R1 upon R2. So Q1 dash may also be written as R1 upon R1 plus R2 Q1 plus Q2 dash,
Yeah. Okay.
and same for the Q2. So Q2 dash can be written as R2 because constitutes R2,
Yeah.
and R1 plus R2, this fraction of the total charge.
But this one, it tells us the ratio, right?
It will tell you the absolute value, this is the total charge,
Okay.
like 10 coulomb something. So 10 coulomb into this fraction, which will be something, it will be always be less than 1.
Okay.
It can be 0.2, 0.3, 0.5, 0.9, whatever, depending on if R1 is greater or R2 is greater. So whatever will be the greater, that will take the larger portion. If R1
Okay.
is greater, that will take the large fraction, because let's say assume R1 is 10, R2 is 2, let's say. So the sum is
Okay.
12, but in case of Q1, R1 will take the larger value and the fraction will be more close to 1. It will be like 0.9 or 0.8.
Yeah.
So that will take the larger part, Q1 dash.
Okay.
It will tell you the absolute value of it. This was
Uh,
telling you the ratio. Okay.
yeah. Okay. Oops.
So that's how it is. But also, final thing to just finish it off, we want to find the value of common potential. Okay, V that it has got after the connection.
Yeah.
So after connection, I told you that the potential will be the same. They will have the same potential. All
Yeah.
right.
Okay.
Now we want to know what that potential be. Okay. Because for
So.
individual it was some V1 and V2, isn't it? For Q1 it
Yeah.
was V1. But we want to know the common value. What will be the common value? Okay. So how can you tell that? See, in general, Q is equal to CV and V will be how much? Q by C.
Let's keep on to you.
So in place of Q, we can write the total charge Q1 dash plus Q2 dash, because that is,
Yeah. Yeah.
we are talking about the common one. So that we need to take the sum, right?
Yeah.
And inside the here denominator, we can write the sum of the capacitances C1 plus C2. That's it.
Oh. Okay.
Yeah. This will be the value of common potential. Okay.
Yeah.
But individually, when it was not connected, it was something else. It was V1 is how much? Q1 by C1, and V2 was Q2 by C2.
C2. Yeah.
So that's how distribution of charge takes place. We'll do a question on it, I think.
Okay.
But let us finish the theory first. Oh, I have also another thing to tell you in this, but we'll not prove this. We'll just write the final result. Okay.
Okay.
Now let us talk about whether there is some loss in energy when this happens, like before and after. Because charge conservation is a different thing. Charge
Oh,
conservation is there. We know that Q1 plus Q2 is equal to Q1 dash plus Q2 dash. But whether or not there is some energy loss on or or not, how can you tell that? You need to find the initial and final energies and match them,
with
compare them.
the okay.
So initial energy, let's say, is U1 before connection, which will be the sum of the individual energies of each one of them.
Yeah.
So half C1 V1 square plus half C2 V2 square. Now after connection, the final energy is half. Potential is same for both, so V square, isn't it?
Yeah.
But inside the bracket, C will be how much?
No.
C1 plus
Oh,
C2.
C1 dash. Oh, is it gonna be dash?
Dash is not there.
Oh, okay.
C. Capacitance value is not gonna change for individual, remember. C is 4 pi epsilon naught r. Rho radius is never changing. C1 and C2, there is no point in even taking C1 dash and C2 dash into consideration now. Because there will
No.
anyway be equal. C1 will be C1 dash. How, why take that, right?
Oh, yeah, okay.
Because it depends on radius. Radius is for both cases R1 and R2, R1 and R2. So there will be some loss in energy if you analyze, because we need to take some time to do that. Alright?
Okay.
So upon doing this, you will get some loss in energy. Alright? And that
Yeah.
loss in energy is denoted by del U, which is, you can directly write the formula C1 C2 upon 2 C1, because you won't be asked the proofs in exam. This thing,
Okay.
there is a loss in energy. Okay.
Okay.
So this is a whole square, isn't it?
Yeah.
C1 and C2 will always be positive. Capacitance value is always a positive. So this is positive. Everything here is positive, and whole square value will always be positive. So that del U is always be a positive quantity.
Okay.
Or either it will be in like the, it will be either 0 or positive.
Okay.
Okay, so that's how it is. All right.
Mhm.
Just a second. See,
Okay.
so this is done. So there are some topics in bits and pieces. We'll be taking that because like you'll not get the flow, but they are still there in the syllabus. So capacitance of a parallel plate capacitor with and without dielectric inserted between the plates. Suppose we have a capacitor, parallel plate capacitor. Its capacitance is C, which is epsilon naught A upon D. Alright.
Yeah.
Now if we have another capacitor, Okay, so that capacitor, in that capacitor, okay, let's take this thing. So inside this we have placed, instead of air, see it was air in this time,
Yeah.
we placed some material of dielectric of permittivity epsilon naught r, epsilon r, right?
Okay.
So in that case its capacitance would be, let's say, c dash, it would be equal to epsilon naught epsilon r a by d, is it?
Yeah.
But what happens if the case is something like this? So this is the capacitor, I'm drawing it maximized so that it is easier to see. The total is d, okay,
Yeah.
and inside some part of it, let's say up to here, okay,
Yeah.
in the thickness t, this is t, we have inserted the dielectric.
Wait, what's a dielectric?
Dielectric will learn it in the separate class, but it's something that's not a conductor, okay,
Oh, okay.
it may be paper, okay, mica, any insulating material,
Okay.
all right,
Yeah.
like you don't not a pure conductor such like a copper or iron, aluminum, like that.
Okay.
Dielectric is in fact an insulator, okay,
Yeah.
kind of insulator. So we have inserted some paper here or mica here, so that means that air is not here, okay. In
Yeah.
this part of the capacitor it is still air. Now we want to know the capacitance of this, all right,
Yeah.
so we need to know the formula for that. And further it is given that this dielectric has a permittivity of k instead of epsilon r, or you can also call it because it's a constant, I told you, no,
Yeah.
epsilon r and k is used interchangeably in books. The formula for that is epsilon naught a, okay,
Yeah.
epsilon naught a upon d minus t, what, d minus t, what is d minus t? See, d is the whole length,
Yeah. D is the whole thing minus the.
t if you subtract the air remains,
Yeah.
so this is for the air part, right? So air part
Yeah.
we don't do anything, just like the simple thickness is there, okay,
Yeah.
but for this part which constitutes dielectric we will have to introduce this. So t minus t plus t, that part that constitutes dielectric, t divided by the dielectric permittivity, electric permittivity, which is
Okay.
k or epsilon r, both are same thing. This is the formula, this is very important, you get this very often in exams.
Oh, okay.
Now there are some uses of capacitors. So capacitors are used in fact many places, in industries and homes, everywhere. In fans we use that.
Yeah.
And fans like ceiling fan.
We use capacitors and ceiling fans.
It's right up there, the white color, like some slender type of thing you might see. Slender of white color, it is a capacitor.
Oh.
Haven't you seen
No.
ceiling fan? You look at that and you might see a white colored cylinder.
like for which is hanging,
Yeah, and it is also used in radios, but they are not found as of now. But radios, FM radios use.
I know those.
Yes, it is found in when you change the station by there's some dial that you use to change the.
Yeah.
So that is composed of capacitor.
Oh, cool.
Many places in motors you find that submersible motors, pumps, many places. Okay,
Yeah.
so this is it, I think. Okay, let's finish the last topic, because then we'll be relieved of it,
Okay.
except of a dielectric thing, but that will take a separate class. So the last thing is, the topic is, let me write it, effect of change in capacitance on its charge, potential difference, or you call voltage, electric field, and energy that is stored.
Okay.
This is the topic. For this, we will take two cases. So, case 1, suppose we have a capacitor of value C and the battery of volt V connected to it. Okay,
Yeah.
so let's say the charge on this is Q, the potential is V, the energy, and no, not the energy, the electric field is E, and the energy is U. I've mentioned everything.
Yeah.
Okay, now initially, so when battery remains connected, battery will remain connected all the time. Okay, in the case first is when battery remains connected, and what we will do is, and D is also constant, remember. Okay, this D, so D is also constant. Now what we are gonna do with this, we are gonna insert a dielectric,
Yeah.
or you can say
Okay.
an insulator. Insert a dielectric of epsilon r inside the capacitor with the voltage or the battery still connected to the capacitor, right?
Yeah.
So we do
Okay.
that. The voltage is still connected, the source voltage. Now we have inserted dielectric of K or epsilon r, whatever you call it. Okay, now
Yeah.
after insertion, what will happen to each one of charge, capacitance, voltage, electric field, and energy stored in the capacitor, that we want to know. This is the
Okay.
question. All right, so what will happen, you tell me. See, if C
Like,
dash
have
Q
we
dash,
inserted a dielectric in the whole area?
yeah, that's the whole area in this case. Q dash, whole area is exposed, and the now modified values, let's say, are these dashed values. All right,
Yeah.
so C dash will be how much, can you tell me? Initially it is epsilon naught A upon D, isn't
Yeah.
it?
Yeah.
And when
So
you
this
insert a dielectric inside a capacitor, what happens? I just told you it is epsilon naught epsilon R A by D, right?
yeah.
And if you take epsilon naught A by D separate, you can replace, so this is C dash, I'm sorry. So C dash will be epsilon naught epsilon R A by D, and you replace this thing
C
by
into
C.
ER.
So C into ER. That means the capacitance in this case will be greater than C because ER epsilon R is being multiplied to it. And epsilon
Yeah.
R value is always greater than 1. So C dash will be KC or epsilon RC,
Yeah.
and that will be greater, so C dash will be greater than C.
Yeah.
So we have sorted out C dash. Now what about all of these? Q dash, V dash, we need to know each one of them. So for V dash it is very simple. See, the battery is still connected. Same battery is connected. So there will not be any change in potential with between the capacitor's plate. It will still be V, right?
Yeah.
Because the same battery is connecting
Yeah.
here. So V dash will be V. It is sorted. This is very easy. But what about electric field? E dash. See, electric field. I told you what is electric field. E is equal to
KQ.
dV by dr.
What?
So electric,
Uh,
isn't it?
yeah.
Just a second, I'm getting a call. So we were talking about the electric field. So
Electric. Yeah.
electric field is dV by dr. So it is actually electric field is voltage divided by, this is meters distance, right? So D,
Distance.
E is V by D in this context because D is this distance,
Yeah.
right? Let's say E dash is also V dash upon D dash initially, right? Because we don't know what
Yeah.
will. Now V dash is V, so we can replace this with V, and D dash is also D because we are not changing the thickness of the
Distance. Yeah.
capacitance. So V by D. This is equal to E, isn't it? V
Yeah.
by D is the initial
Yeah.
E, so E dash is just E. There is no change.
Uh,
So till now we have found that only capacitance value has changed. Voltage is the same. The electric field is the same. Now what about the charge? Q dash. So let's say Q dash is some C dash into V dash,
yeah.
and C dash is K into C.
Yeah.
V dash is V. Can we say that this is equal to K into initial Q?
Yeah.
Because C into V is initial
Yeah.
Q.
Initial Q.
So Q dash has also increased to K times Q.
Oh.
Now finally, what we are left with energy. The energy, let's say, is U dash, which is half C dash V dash square, and that will be equal to C dash is C KC, right?
Yeah.
V
KC.
dash is just V, so V square, but half CV square is the initial U, so
Yeah.
KU, that means energy has also increased by an
K
amount
times.
K. This is the first case. Okay, so capacitor value has increased. These both are there. They're just the same. Q is increased and this is increased. Now case 2. Case 2, when battery is disconnected, okay, after charging, and then capacitor capacitance of capacitor changes. Let's see what will be the case. So here again we have a capacitor connected to a battery of V volts.
Yeah.
So their values are respective values are these. All right, each one for.
Yeah.
Now battery is disconnected in this case. All right. So first what we do is we have disconnected the battery. After charging, remember the battery initially was connected, the capacitor charged to a value so that it has energy U, isn't it?
Yeah.
And then the battery is disconnected, and then after that the dielectric slab is inserted.
Okay.
All right.
So, okay.
So battery is disconnected and then a dielectric slab is inserted of a value at the permittivity K. So in this case, let's say the respective values are C dash, Q dash, V dash, E dash, and U dash. Right?
Yeah.
Now what can you say about the value of capacitance? Capacitance is anyway gonna increase because as soon as you put in some K, its value is gonna increase no matter whether you have a battery connected to it or not. So K dash will be Kc, isn't it?
Yeah.
Because it will invoke the same relation, the epsilon naught A upon D. And when C dash will be there, this will be epsilon naught Ka upon D. Same thing. So we'll take this common and then replace it with C, and then we'll get this epsilon naught R in multiple.
Yeah.
Alright? It has nothing to do with the battery, the capacitance. Now, what do you say about the charge? So Q dash will be how much? See what the capacitance was initially charged to some value, right?
Yeah.
It has hold of some charge Q in it, and now the battery was disconnected, and now this capacitor or the dielectric is inserted, which is some insulator. So
Yeah.
there is no way we are gonna get some additional charge here because no electric
Yeah.
process is even taking place. So Q dash will be the Q only.
Yeah.
Now what about V dash? So V dash will be, see, the
Same?
Q is equal to CV. Let's see it's same or not. So V dash will be Q dash by C dash.
Yeah.
So Q dash by C dash. Q dash is Q, C dash is KC, and this Q by C is the initial voltage. So we can say that V dash is V by K.
Yeah. So it's not the
So
same.
it has downscaled,
Yeah.
it has decreased.
Okay.
Now going further, we want to know what the value of E dash is, and E dash will be used using this relation V dash by D dash. V dash is V by K, D dash is still the same because we are not gonna change thickness of it.
Yeah.
V by D can be replaced by E, and the K is still there. So E dash is E by K, and it has also downscaled.
Yeah.
Further, finally, we need to find what the energy stored in the capacitor is. So it is half C dash V dash square. C dash is how much? It is
C
Kc.
dashes.
V dash is how much? V by K.
Yeah.
K cancels out. Oh, sorry, this should be V square. So K cancels out, right?
So it's half V
Half
squared.
CV square,
It's
which is the initial
the
U.
same. Yeah.
Am I doing something wrong? Yes, definitely I'm doing something wrong. See, let's do it again.
Okay.
So this is half, C dash is KC, and V dash is how much? V by
V
K,
dash V1K.
that's
Yeah.
whole square. So half KC into V square by K square, right?
Yeah.
So 1K will get
And it
cancelled out.
cancels. Oh, okay.
So U dash will be U upon K. This is also downscaled, right?
Okay. Yeah.
So this is the analysis of the two cases respectively. When you insert a dielectric between the plates of capacitor with this source first connected all the times and then
Yeah.
disconnected in the second case. So this is it.
Okay.